Here's sodium chloride. Chlorine is shown in green and sodium is shown in purple. Chloride is a negatively charged ion and sodium is a positively charged ion. When you look at this substance, you can see that it's an ordered compound and it's kind of difficult to look at. You get lost after a while looking at all of these balls orientated in space. If we display the ionic radii as van der Waals spheres, you can see that there's an alternating arrangement of negative, positive, negative, positive, negative, and positive, and that's for any kind of orientation. So if we look at this way, we can see negative, positive, negative, positive, negative. Each of the negatively charged ions is attracted to the positive ions through Coulomb attraction. So opposites attract, so you have negative next to a positive for this crystalline substance. Okay, now we're looking at solid sodium chloride again, and it looks like it's jiggling around. At room temperature, this solid does not show mobility of the anions and anions, but there is molecular motion. If we take a look, if we add some water molecules to this, we can actually watch the substance dissolving. Let's go ahead and display the charges, and we can see that the positive charge from the hydrogens of the water molecules attracts the negatively charged chloride ion. And if we actually display those interactions with a dashed line, we can see that water molecules surround chloride in a different way than it does sodium ion. And we'll take a look at that right now. So we can see the chloride here is a negatively charged ion, and it's electrostatically attracted by the positive charges or the partial positive charges on the water molecules, whereas sodium ions are attracted to the negatively charged on oxygen atoms from the water molecules. This is called an ion-dipole interaction, whereas these dashed lines generally are showing hydrogen bonding interactions. Here's chloride in the middle in green, solvated by several water molecules. It's hard to see when we look at the van der Waals surface, but if we show a ball and stick model, it's somewhat easier to see. Chloride is negative, so you can see that it's surrounded by hydrogen atoms in the cage from the solvent shell, just due to electrostatic attraction between the delta plus on the water molecule from the hydrogen and the negative on the chloride. If we display hydrogen bonds, we can see that the individual water molecules are held together by hydrogen bonding, so that's also an attractive interaction there.